Okay. Okay, so as I said yesterday, the main focus of setting up all of these networks, the two different kinds of networks, the ultimate aim, I should say, is to try and understand how granular materials respond to external stresses. So why do these force chains form? Is there what is fundamentally responsible for them? So what we would like to understand are these old experiments from 2001. And I'm sort of bringing this back. This was an active field of research to so how stress gets transmitted in granular materials. Around 2000, from 2000 to about 2010, and then most of the emphasis in the theoretical community has gone to understand the jamming transition, but not stress transmission in jammed states. And so I'm sort of bringing the focus back into that. So what I'm showing here are experiments from the group of Bob Berenger in 2001. And on the top left, A is a pile of grains. It's quasi 2D. So these are photoelastic. Karen's talked about this, and you have played around with these things, right? So you know what those are. So you see those force chains, right, which form under gravity. So this is the as-prepared state. And then the B is one of the grains has been poked a little bit. Okay? And you see the resulting pattern. And C and D, so C is the response, so B minus A. Okay? And D is just another realization, built exactly in the same way, doing the same thing and showing the response. Okay, so what this response shows is that the stresses seem to get transmitted along specific paths, right? And that's what the challenge is, to try and understand. So one of the important things that was noted by these experiments is that, and again, as must be clear by now, we should really think of responses in an ensemble average sense. So I should keep doing this over and over again and ask what the response is. So these are ensemble average responses of packings created in 3 different ways. And the left-hand packing is an ordered arrangement of the grains. So the network that I talked about, which is the contact network, is regular. Okay, it's a hexagonal packing of grains. So the contact network is regular, and these are the ways the forces now get transmitted. So repeated experiments on that same hexagonal arrangement of grains, and this is the pattern you see. And you do see, even in the ensemble average pattern, these traces of paths. It's more like a wave propagation than sort of elastic transmission of stress. If you increase the disorder, these things tend to get smeared out. And this is the most disordered one that they created. And it looks more like a diffusion. If I thought of this as injecting a random walker there and asking what's going on, then it's diffusing. So one of the challenges has been to try and understand the relationship between the disorder in the underlying contact network or the underlying real space arrangement of grains and their response to external forces. Yes? So, yes, this is polydispersed and this is polydispersed pentagons. For a given packing, just repeated experiments. You just poke it with different times. Yeah. So you, just like Karen was doing with her experiments, you release the force, and you do it again. So the same packing of the same bead that I don't know. That I don't know. Okay, but this is one example. It's known that the underlying contact network So the basic question that we'll hopefully get to by the end of today's lecture is, how does the disorder in the underlying contact network, can we create a formalism which tells us how the disorder in the underlying contact network affects the response to an external perturbation? Okay, so we'll try to create a theoretical framework for that. So yesterday's lectures introduced some of the tools that we need, and we will come back to that. But what I'm going to start talking about today is the whole area of how to think about stress transmission in granular materials in contrast to elastic bodies. Okay? But just as a heuristic, I'm just going to draw this picture here. So yesterday I introduced two different kinds of polygonal tilings, right? One was the real space tiling, which had to do with, and then there was the force tiling. So I'm just going to heuristically, or in a very toy model-y way, try to argue that the constraints of force tiles, sort of naturally, the constraints that are naturally imposed by the force balance conditions, which led to the force tiles, you can roughly think why that has to lead, if those were the only constraints, that has to lead to an organization of the forces. So I'm going to give you a simple toy model and say, let's assume that every grain has 4 contacts. Every grain has 4 contacts. So all of my real space polygons are 4-sided. And let's say if the forces, so each grain has 4 contacts, and the force tiles, right, that I'll construct here are made out of putting these forces head to tail. So F1, F2, F3, F4. And that's what led to the points, which were the heights, etc. So let me also demand, I want to make this as simplest as possible, that these force tiles, so this is grain 1, and the force tile of grain 1 I can make by any kind of, so let's make this frictionless. So I say the forces have to be along the normal. And then my force tiles can only be or rectangles. Right? I can make them rectangles. Right? They can be squares or rectangles. Okay? So let me put down here, let's say, so arbitrarily I have picked some origin, 0, 0, right? And I'm going to put down one rectangular tile here. Okay, let's say that's grain 1. And I have this perfect edge matching condition that I need to match. And I'm allowing you only rectangles. So let's try to, so this is grain 1, and let's say this is grain 2, which is in contact with that. And I'm going to put another rectangle down there. It has to match this edge, though. So the best I can do if I want to make it disordered is play around with this length. Right? So I can keep doing this. All I can do is that, right? I introduce some disorder this way. But because of this edge matching condition, that's the most I can do. And now once I have done this, what can I do here? So again, so I can introduce disorder in this direction, but these edges need to match, right? So I can make this maybe very big. But then as soon as I do that, this is that, right? So you can get the picture. So what I'm saying is, in the force tile picture, force chains are contacts that bear large forces. Right? So if these forces are large, then in Karen's pictures of force chains, the force chain would go through here. So here, what am I saying? That as soon as I have one large force, they have to line up. Just this, the geometrical constraint of edge matching gives you a rough picture as to why in these systems forces have to get organized in a particular way. And we have done a lot trying to understand how these forces get organized, et cetera, to try to understand the jamming transition, and I'm just completely avoiding that. I'll put some more references in for you guys to look at. But this is a heuristic, hand-wavy argument saying just these constraints tell me that there's a force chain lying here, right? And then these forces are all small.
So you're arguing this for crystal?
I'm saying this is for, yeah, I'm saying this is a four-sided. It doesn't have to be a crystal. It doesn't have to be a crystal. It just, every grain has 4 contacts. Every grain has 4 contacts, and I'm saying all I'm allowing the force tides to be are rectangles. Right? So in this case, yeah, it's a crystal. But
So the force chains in this case are all just vertical horizontal.
correct. So the other message from this is that by looking at my force tiles, I can actually get, without any thresholding, by seeing where the large edges are, I can draw the force chains, and I don't have to, I can characterize the full force network by looking at the arrangement of these contacts. Okay, so for example, since I mentioned this, and I showed this yesterday, let me see if I can pull up one where I can show you the force chain. Oops, stop. Okay, so let's just look at this. This is a force tile constructed from some system that's force balanced and jammed. And what you see are these large forces, and then the red ones are the small forces. And you clearly see that there's an arrangement. There's sort of a lamellar structure to this, right? So this is how force chains show up in this tiling picture. It's saying there's a force chain here. These are all large forces, right? But instead of saying qualitatively that there's a force chain, we can actually characterize what the geometry of these patterns are and get a more comprehensive description of how the forces are organized. Okay? So I just wanted to say that one of the advantages of this representation is that without any kind of thresholding, you can look at the force pattern. And you see these characteristic regions of large forces, regions of small forces, regions of large forces, regions of small forces. Okay, so I'm now going to go back to the main topic for today. But this is just a heuristic argument, and what we are trying to do today is try to get a better understanding of where these things emerge from. So to begin with, I'm going to talk about, and if I'm not writing large enough, please yell. So to begin with, we're just going to think about how we think about stress transmission in elastic systems. So let's say I have an elastic spring network, and I'm going to coarse grain it and ask about how stresses get transmitted. And I'm going to look at a 2D system. This is my coordinate system, and there is gravity in this direction. Okay, and that's the only force acting on this system. The only external force acting on this system. So then I want to write down the equations for momentum balance or mechanical equilibrium, which is, someone said something.
All the forces sum to 0?
Yeah, but the continuum version of that, if I told you I have a continuous elastic medium, zero or something else. I have external force. I have gravity. So the divergence of the stress tensor is equal to G. Rho is 1 or M is 1. Okay? In the Z direction, so Y direction. Right? So How many equations do I have? I'm going to write this out explicitly. That is equal to G, right? And del y, sigma yx, plus del x, sigma xx is 0. Those are my equations for the stress tensor. Just imposing, this is macroscopic momentum balance. How many equations do I have and how many unknowns do I have? I have 2 equations. How many unknowns? I'm doing 2 dimensions, so the stress tensor has 4 components. What do I know about it that reduces that? It's symmetric, so sigma xy is sigma yx. And why is it symmetric? From a torque balance. So I have 3 unknown components, and I have 2 equations. So I can't solve this equation without knowing something else about the system. And what I know about the system, in addition to this, is I'm looking at linear elasticity. So sigma ij is some Cij KL epsilon KL, where that's the strain tensor. Okay? And the strain tensor is defined in terms of what? Think in terms of a spring network or whatever. Strain tensor is displacements, right? So it's defined in terms of the derivatives of the displacement field, and the displacement is taken from what? From a reference state, which is the ground state of my elastic system, my spring network, in the absence of any imposed external forces or stresses. Okay, so there is a for me to do this, I need to have a well-defined reference state. Is everyone? Yeah? So just because of the fact that the strain tensor is constructed from the derivatives of the displacement field, there are some conditions that the strain tensor itself has to satisfy. It's just the fact that it's constructed from the derivative of this. And those conditions are called compatibility relations. So if you guys have never worked this out, this is homework for when you guys get back home or whenever, to show that this has to be followed if I have a tensor which has this one. Okay, it's because the tensor is a derivative of these vectors, then it has to satisfy this. So that gives me the closure. This is a third equation now, which I can put back in here and get closed. So just from counting, I now have 3 equations for 3 unknowns, because I can use this to eliminate the strain tensor in favor of the stress tensor, put it back, and I have a closed system. So if I put this in, Let me write this here so that the elastic thing. So if I incorporate this into these equations, then I get an equation for the stress tensor, which is for isotropic elastic systems. So this is what? This is the elastic modulus tensor, right? And the nature of the elastic system, whether it's isotropic or anisotropic, etc., is all incorporated in here. So for isotropic elastic systems, I get the following equation for the stress tensor. And that if I have anisotropic, then it doesn't become a complete square. There are other terms in there. But I now have a closed form equation, and now I can solve this given boundary conditions. So that's how I would solve the stress transmission problem for an elastic system. So what I needed is this relationship and the compatibility relations, which were based on the fact that I could define a strain field from displacement fields from a reference state. Okay? So now, if I want to do the same thing okay. For a granular system, can I follow this procedure based on what I've been trying to tell you guys?
What was your reference?
Correct. So the main problem is there's no reference state. So the stress-free state is ill-defined, which tells me I have no reference state to start from. So then there's been a whole body of work, which I will review briefly, which then said, okay, so the only option we have is to try and construct a stress-only description of stress transmission. And if you look at the reading materials on the web, there are these lecture notes by Jean-Philippe Bouchot, and that it's beautifully covered in his lecture notes as to where the history of all of this. So what we want to do is get rid of this concept or work without the concept of a strain field, because we don't know how to define that. So there's the stress-only approach. And the genesis of all of these approaches lies in a particular model called the Q model, which I will review, and then I'll try to show how, from models like this, what you can do is constrain the stress tensor in the following way. From any of these models that I'll talk about, you'll get some relationship between the components of the stress tensor, which is demanded by the conditions of force balance. And if I have one condition, that's it. That's all I need. I need a third equation to close this, sticking to 2D. Okay. So the Q model was developed by Liu, Majumdar, Beaton, Coppersmith, and I might be missing someone, in 1999. There's a science paper, there's a PRE, it's all reviewed in that Bouchot review article. So the approach that they took, and which one can then generalize, is to say that let me take the underlying network to be a crystalline lattice. So they are looking at this. Okay, so the underlying network is crystalline. But because I have this indeterminacy of the contact forces, I will put in, we're going to write down a stochastic model. And the stochasticity in the model, the randomness in the model, comes in how stresses get transmitted across the contacts, even for this ordered packing. So I'm going to draw an ordered packing of the following kind, where each, and so again, we are thinking about gravity working in that direction. I'm looking at a two-dimensional system. And I'm going to label these because it's a regular lattice. I'm going to label the weight carried by each grain by Wij. Okay, so Wij is the weight at each point. And the way we are constructing this regular network is that every grain has two neighbors in the row below it. Okay? And then the rules of the Q model are as follows. I look at this grain, and it has some weight, and I'm going to say it's going to distribute its weight to its two neighbors with some random weight, with Q plus Q minus being equal to 1. Okay, so there's a total weight, let's say, of W here. It distributes that to its two neighbors with a weight of Q plus and Q minus. And Q plus Q minus is going to be equal to 1 because the weight has to get distributed to one of its neighbors. I can make this have more neighbors, and then there will be many more Q's, but 2 is good enough for us. Okay, so then can I write down an equation for this? So I'm trying to write down an equation for what is W at a site I and a site J by relating it to the W's on the row above. And each grain, let's say, has the same mass, so there is some W naught that each one of them carries. There's no disorder in there. Okay, so the only disorder is in the Q pluses and Q minuses. And I have the constraint that Q plus Q minus has to equal 1. Okay, so help me write down this equation. So W at Ij is going to be W naught plus Q plus. And Q plus depends on the I and J. It's a random variable. So Q plus of I minus 1 and J minus 1 times Wi minus 1, J minus 1. And I have moved too far to the right for you guys to see this. Okay, let me write this below here. Wij is W naught plus Q plus I minus 1, J minus 1, Wi minus 1, J minus 1, plus Q minus I plus 1, J minus 1, Wi plus 1, J minus 1. Does this equation remind you guys of any other equations that you have seen? Let's try to draw some paths. Yes. let's try to draw some paths here and see what happens, right? So let's take the simplest situation, which is actually the most anomalous, but let's try to do that to see what these things might look like. Let's say that every grain can choose only this to be 1 or 0. So it can either transmit all its way to the right or to the left. So if I can think of this, then it might go to the right here, might go to the left there, can keep going to the right. So these are going to be, so each of these is like a random walk, right? And I'll have coalescing, so this might coalesce at that point, right? So I'll have a whole set of coalescing random walks. And so this is nothing but writing down the master equation for the distribution of a set of random walkers propagating in time, if I want to think of J as time and I as space. So you can imagine what the coarse grain stress transmission might look like in this model. What would it look like? So because it's a random walk, it is diffusive, and it turns out that for any choice other than this this is sort of a critical choice where Q can be only 1 or 0, you can work out a generic set of properties. And what you can work out, let me keep that up there. Okay, so what did we incorporate into this Q model from the perspective of force balance? The equation that we wrote down is nothing but force balance, but it's a scalar force balance. We're assuming that only the vertical, there's no horizontal force ever. Right? So this is a scalar force balance model. So this is called the scalar model or the Q model. Right? So I have only considered force balance in the direction that I have an external force in. I have completely ignored the vectorial force balance nature. Is everyone on board with that? Okay. So a few things you can do with this. So one of its biggest success was explaining a generic exponential tail in the distribution of forces. So I don't know if Karen talked about this. Did you talk about the? Okay. So one thing when physicists started looking carefully at the distribution of contact forces in a granular network, one of the surprising things was that distribution was not Gaussian. The distribution had an exponential tail. So one of the successes of the Q model is that you can, from this model, one thing I can compute is the distribution of the weights at the jth level. Because it's a random walk-like process, you can go back, you can take a particular distribution of the Q's, and if you take a particular distribution of the Q's, you can work this out. And this is what was claimed to be, or shown to be, robust. So for any distribution of Q's, except for this 1-0 distribution, this has an exponential tail. And I'll write down the expression, which is the simplest one, when I take a uniform distribution of Q's. So I pick Q plus minus from a uniform distribution with the constraint that Q plus plus Q minus is equal to 1. If I use that distribution, then what you can show in any of these cases is in the limit of J going to infinity. So this is like time going to infinity. If I think of this as time and this as space, it reaches a fixed point distribution. It reaches a distribution that then no longer changes with j. And that distribution, so I'm going to call that p star of omega. So it no longer depends on j. For this uniform distribution is omega star divided by the square of the average of the square of the weight. So this was one of its biggest successes, and that you could work this out analytically. Yes?
So if at each level we introduce another W naught,
then it becomes more complicated.
yeah, so this only holds when W naught is actually 0.
No, no, no. This is with W naught. W naught is the same. W naught is the same for all grains. So I'm actually looking at that equation and solving it.
So why does the W not diverge?
Oh, I'm scaling it by this. So that will diverge. Did you get?
Yeah.
So omega naught will enter, and it will diverge if I make j go to infinity. But if I scale it by that average weight, that's the distribution, then that's invariant. Okay? So yes, this will diverge. It's just like diffusion, right? If I look at an infinite time, my width is going to become infinite, but I have a distribution that's a Gaussian that I can always scale by that width. So here, this distribution is an exponential scaled by the weight at that j. So I should put in a j here. So that was his biggest success. Now you can ask a little bit more and ask, what is the coarse-grained equation for stress transmission that you get from here? Right, so I've written down this. So now I can ask, what is del y of W? And so I don't have time to go into deriving these, but so what you end up with is going back to, so there is some density, which is what's capturing in my continuum sense the W naught. And then all I have is a diffusion term. Now, question, the coarse, and this is for, this is, the simplest one to work out is when Q plus is equal to Q minus equal to half, which is like an unbiased random walk. So for the unbiased random walk, when I coarse grain this, you can probably see just by looking at that equation and thinking of coarse graining that I'll end up with diffusion. And D naught depends on the kind of lattice I'm using. Do I have 2 neighbors, 3 neighbors, 4 neighbors, whatever, it's some effective diffusion constant. You can also take this and disorder it. So say Q plus and Q minus are not exactly equal. There is some stochasticity in it. So that's going back to that and making Q plus and Q minus depend on I and J. But make it vary smoothly, so it doesn't vary too much from one layer to another. Then you still get the same form. So the stress is still diffusing, but D naught gets replaced by another, so some constant here that depends on what the width of this noise is that you're adding to Q plus Q minus. But the upshot of all of this is that if I take this lattice of grains and I take scalar force balance and make the Q plus Q minus chosen randomly, then my stress transmission is diffusive, which is inconsistent with that picture. right? This is an ordered arrangement of grains. And in ordered arrangement of grains, you don't see. So if this was true, this is what I would see. So this is like putting a delta function here, right? And just like a delta function around the probability distribution in a random walk will become broader and broader. If I put a delta function at the top of my pile, it should just broaden out. So the Q model's success was in getting the exponential distribution, but the spatial transmission, the fact that there are, the observation of chain-like structures did not get captured by the Q model. So then the next step in going beyond this, again, the whole idea in all of these approaches was I'm going to take some network and I'm going to consider the contact forces to be disordered, but I'm going to impose the constraints of force balance. Okay, so the Q model was the start to it, where they imposed a scalar force balance to see if under any modifications, the Q model could give rise to these kinds of structures. What was then tried was to extend this to again, these are toy models. So what I'm leading up to is that with the formalism that I have presented to you yesterday, we can do better than these toy models in imposing vectorial force balance and seeing how stress gets transmitted. But so the toy model, and here is one example of a toy model with a vectorial force balance. And before I explain the model to you, I'll tell you why the result of it is interesting. As soon as you impose a vectorial force balance on a Q model like model, where I have an ordered arrangement of grains, what you find is that there is now a relationship between the two components of the stress. Vectorial force balance then demands that the only way you can satisfy vectorial force balance, not just scalar force balance, is by introducing a relationship between the two components of the stress. And of course, if you have something like this, I have a closure relation, and I can solve the stress equation and see what I get. Okay? So I'm just going to schematically tell you what the simplest model that gives you that relationship is. And it turns out that I actually need, so this is again a Q model like structure, but this now has three neighbors to it. And instead of just being characterized by a weight, each ij is now characterized by a horizontal force and a vertical force. Okay, and then you do the kind of thinking that we have done for the Q model, and say these forces now get distributed in some stochastic random manner to these grains. And the assumption that was made in this toy model was that the forces only get transmitted along this direction. So there's an angle here that characterizes where these are. So it's a sort of frictionless contact. So I have still two components. I'm introducing two components of the force, but the component of the force that gets transmitted along here is assumed to be along this direction. Okay, just to make things simpler. So now, then so that's one assumption. So frictionless contact. And the second assumption, or the second ingredient in the model, is that you assume that a fraction p of the vertical weight gets transmitted to the grain at the bottom. Okay, so the randomness is going to come in how the vertical force gets transmitted. Okay, so the vertical force, a fraction p of the vertical force gets transmitted to the grain directly below it. Q plus, again, now refers to how much of the vertical force is getting transmitted, becomes 1 minus p times 1 plus some epsilon over 2. Okay, so if it was 1 minus p and epsilon was 0, then this would have to be 1 minus p over 2, and that would have to be 1 plus p over 2, because the sum has to be 1 still, right? So I'm introducing a parameter in the model So if I didn't have the horizontal forces and I had only vertical forces, this is like doing the Q model. Okay? But now I have this parameter epsilon, but now I'm going to insist on the balance of both the horizontal and the vertical forces. And if I insist on this, both FH, and what does that mean? That on every grain, the FHs have to sum up to 0 and the FVs have to sum up to 0, right? If I insist on that, then again, I'm bypassing this calculation. What you find is epsilon cannot be 0. What you find is that epsilon depends on this angle, and it depends on the ratio of the horizontal force to the vertical force at that site. So this is just taking these distributions of the vertical force and saying on each grain, I am insisting that the FH is sum to 0 and the FV is sum to 0. Yeah?
We're still only putting gravity in the y direction.
Yes.
Okay.
Gravity is still only in the y direction. So what you see is as soon as you put an FH in here, however small it might be, it's telling me that epsilon cannot be 0. And if epsilon cannot be 0, what is it basically telling me?
Anisotropy.
Yes. So it's telling me there's a preference for the vertical force to get. So if epsilon is positive, this transmission coefficient is larger than that transmission coefficient. So as soon as I put in a shear, if you want to think of it that way, if I allow for a horizontal force and insist on vectorial force balance, then there's a preference for sigma in the y direction to get transmitted more along the direction of the horizontal force. And that gives rise to that relationship. I can work that. So what I haven't shown you this, but what I have shown you is that there's a bias in the propagation of the vertical force along this direction if FH is pointing in this direction. If FH is negative, which means it's going in that direction, then it's a bias towards that direction. Okay? Okay, let me move here for you guys. So we can work out the continuum version of these equations. And I'm seeing new faces now that I have moved to this side. So we can work out the continuum version just like we did for the Q model for this model. And this is what I have. And I'm going to write this because I'm going to ask you guys to help me solve this. So A is just the size of my grain. I have to do, for anyone who has gone from a discrete to a continuum, you have to be careful about keeping those microscopic length scales. So that's my microscopic length scale, the radius of the grain. So it looks roughly like diffusion, right? This is what I had in the Q model. But there's this interesting C0 square FB showing up here that came from the fact that I bias the propagation in this direction. And C0 square is (1 minus p) 10 square of psi. So it's a parameter in the model. Okay, so now if I look at these equations, and let's eliminate FH, which I can do, right? How would I do that? I can take a y derivative of this and an x derivative of this, and I can subtract things from each other. And I'm going to ignore these higher order derivatives that I'll get from there. Right, so I have this equation. I want to cancel these terms. So I'm going to take a y derivative of this, x derivative of this, ignore third order derivatives, subtract it off. What equation do I get for FV? I'm going to eliminate FH. So I'll take a y derivative of this, so I'll get a del y square, right? And this will give me a C0 square del x square. What equation is this? The wave equation, right? So just by imposing vectorial force balance, you went from the diffusion equation to the wave equation. And what's a property of a wave equation? It has things called characteristics, right? So there are two characteristics along which the wave will propagate. So this is the simplest model of stress transmission in this random, in this way of thinking. So the way of thinking is I have some ordered arrangement of grains, but I have some indeterminacy in my contact, so I'm going to put in some stochasticity in there as to how these forces are going to get transmitted. And I'm going to ask, if I insist that forces have to be balanced, what do I get out of that? And as soon as you put a vectorial force balance in, you end up not with a diffusion equation, but with a wave equation. And these characteristics then are what? They're characteristic directions, right? Just like I have wave propagating. So these are what would show up as force chains if I looked at transmission. So the wave propagates along these two characteristics. So I will have a two-peaked structure at the bottom, right? So very, very different. So the lesson to be learned from this is that vectorial force balance qualitatively changes the nature of the response, even of an ordered array of grains. And if you take, so there's been much more work along these lines, again, reviewed in Busho. If you take any relation of this form. And there is some function in here which depends on sigma xy squared over sigma yy squared. Any equation like this, any relation between the stress components like this leads to a wave equation. One thing that I want to point out is we have explicitly broken rotational symmetry here. Right? X and Y are not equivalent because I've put gravity in this direction. Right? So rotationally symmetric relations like this don't not naturally lead to wave equations or hyperbolic equations. But as soon as you break this symmetry and you insist on vectorial force balance, it seems to be sort of an unavoidable consequence of vectorial force balance that there are characteristic directions along which the stresses will propagate. Yes, let me. The P of F, it's not easy to work out. I'm actually not sure what it. For the vertical force, it still gives an exponential distribution. Questions? Let me pause. So what have we learned?
Need vectorial force balance to get specific.
So yes, and the fact that we can, the constraint of force balance lets us sort of circumvent using the concept of a strain field and come up with a stress-only description of stress transmission. Because the vectorial force balance is another constraint, if you want to think about it. Instead of having the compatibility conditions that I had for my strain field, I have these constraints now which are vectorial force balance, which for these simple toy models lead to a relationship between two components of the stress tensor. And let me close my equations.
Quick question.
Yes.
So this is not for a disordered system, right?
Well, the idea here in these models, so I will talk about disordered systems in the half an hour that I have left. The whole idea here was the underlying network disorder doesn't matter. And what I'm going to try and convince you guys is that's not true. Okay? What was shown here, though, was remember what this is. This was really sort of going against anything that people believed in. In any kind of system, having an intrinsic disorder in forces for a given ordered arrangement of particles was a completely new idea. Right? Every time, if you thought about any other system that's not granular and doesn't have friction, if you know the positions, you know the forces, there's no more stochasticity left. This is what I was sort of harping on yesterday, that there are two kinds of disorder in these systems. So what these models have done is incorporated in a stochastic way the disorder in the contact forces, keeping the disorder not having any disorder in the underlying contact network. But we should be now able to do better because we have a way of characterizing both the disorder in the contact network and through these height fields, the disorder in the forces. So the question is, if we now insist on take the height representation and ask if I perturb a system or if I put body forces, we had only contact forces yesterday when we talked about it. If I put body forces and I look at that formalism, what can we say about the response of a disordered network? Okay? And we will, okay. Yes, back there first. Say that again? power law force change. What does that mean? Force tails. Only in the Q model, it comes about only when in the critical case, Q equal to 1 and 0. I'm not saying, I have nothing to say about power law distributions of the forces. So what the Q model showed is for a generic Q model, where Q's were picked from an arbitrary distribution, the force distribution had an exponential tail, except for the critical case, which is the 1, 0 case, which had a power law tail. You're saying in actual experimental systems, there are power law tails in force distributions in granular systems? In what kind of simulations? Oh, that's very different. The Q model doesn't get that. Q model doesn't get the low force distribution at all. This is at large forces. The Q model fails miserably for small forces. It doesn't give you that. It gives you only the large force exponential tail. I don't know of any experiments where the large force tail is power law in granular systems. The small force is power law. Okay, so let's now see what all of the stuff that we talked about yesterday maybe can help us with. Oh, yes, sorry.
So if I understood this figure correctly, it seems that it looks more consistent with like a...
With the Q model.
But it seems to have all the aspects of this vectorial problem. So I'm wondering what's the discrepancy?
So the discrepancy is these models are too simple. You cannot really, what I'll convince you is that you cannot take the Q's, the ways, the stochasticity in the force transmission to be independent of the disorder in the underlying network. If you do that, then you either get this or get that. Okay, but also, I showed you, you get that only if you have the scalar force balance. To doing the full vectorial force balance in the Q model actually has not been done. It's been done only in the context of these sort of toy models. Okay? But what we're hoping to understand is why this happens. Okay? And we haven't understood it yet. I don't think anyone has. But what I'm going to try and show you is that you cannot decouple these two disorders. It just does not work out that way, well, if you insist on force balance. Okay, so how can we do better? So what I have to first do, let me draw my picture here because the picture is not so important, but just to set up notation. So I'm going to look at a grain with some number of contacts. I'm going to draw 4 just for simplicity, and I'm going to set up some notation. So this is G0, this is G1, this is G2, G3, G4. So these are my grain indices. And I'm going to introduce my heights, which are now going to sit on these, right? Remember from yesterday? Okay, and I'm going to, the notation I'm going to use is, I'm going to call this, use blue. Call this H1. So this is the current flowing here. This is going to be H2, H3, and H4. Okay? And what I know from yesterday, what I have written down, if you have just body force, just contact forces, no body forces, then the forces have to sum up to 0. And so if I label the forces by the grains that it is at the contact of, right? And G naught is the one that it's acting on. This is what I wrote down yesterday. G4 is H4 minus H3, right? Sorry.
The last one is H1
Or H4 minus H1. So this is what added up to 0. But now, let's think of the situation where I have, let's say, gravity acting in this direction, or I'm going to put some perturbing force, and then the contact forces don't add up to 0. They add up to whatever body force or external force I'm imposing on it. So now I have to have these things add up to negative of, let's say there's a body force acting on grain G naught, they better add up to the negative of that for force balance, right? So the question is, can we extend, so we introduce these auxiliary fields, the H fields, to satisfy vectorial force balance in the absence of any body forces or external forces. Can I now introduce another set of auxiliary fields that will let me incorporate this force balance and will give me some relationship between those extra auxiliary fields that I'm introducing and the body forces that I'm imposing? Okay, so this was all the brainchild of Kabir, my postdoc. So the point is, each contact force has 2 loops associated with it, also has 2 grains associated with it. So let me introduce some auxiliary fields then that sit on the grains. Okay? And I'm going to write this then as phi G1 minus phi G naught. So the phi fields sit here. So there's a phi G1 here, phi G2, G3, G4. Okay? This would be phi G2 minus phi G naught, etc., etc., etc. So now let's sum up the right-hand side and the left-hand side. Could just go there. So on the left-hand side, I have the body force. And what do I have on the right-hand side? I have phi G1 plus phi G2 plus phi G3 plus phi G4 minus 4 phi G naught. Now what is that? What kind of an operator is that? It's the discrete Laplacian. It's the discrete version of a second derivative. So this is the discrete Laplacian acting on phi G naught. And what is this discrete Laplacian? It is, they're called the graph Laplacians for this So for a given network, I can construct it. It's a matrix. So this matrix is the adjacency matrix of this network minus a diagonal matrix whose entries are the number of contacts, the number of contacts of each grain. So it's a diagonal matrix which has Z1, Z2, all the way up to Zn. Okay? So this is now what it's telling me. So what do we have? We are saying if I now impose a body force or any kind of perturbation on a grain, the contact forces will change in response to that. And those change in the contact forces is captured by this phi field, right? So because if I know what the phi fields are up there, I can define new contact forces which then add up to 0. Right? Essentially, the perturbation or the body force changes can be redistributed in a unique way amongst the contacts of the grains such that these new contact forces add up to 0. But the phi field is my response field. So now I can define a big vector, a ket, which is the set of all of these vectors for n grains. So if I have n grains, I have n fields, right? N auxiliary fields that I introduced. And I can do the same thing for the body forces or the external perturbations, whatever you want to call them. This is the set of external non-contact forces that I'm imposing on every grain. And I have the freedom to do whatever I want to do. I can put them only on the top layer. I can put it only on one grain, whatever I want to do. And then the relationship, this response field, then is related to so this is my equation that tells me what the response is. So what we have done is, I have used vectorial force balance. I have not used anything else. But what it's telling me is that the response of the system depends crucially on what its Laplacian is. But this is a symmetric matrix. We have taken this problem and then just now mapped it on to trying to figure out the spectra. So if I know the spectra of this spectrum of this matrix, I can expand it out in a spectral representation, eigenvalues and eigenvectors. I can invert it. When can I invert it to get phi? So I need to invert it to get phi, right?
Is the non-zero determinant?
Yes. So this turns out that there is only one 0 eigenvalue of this Laplacian, and that's because if you look at this matrix, what is this matrix going to look like? The Laplacian is going to have minus Z1 and a bunch of 1s here, but how many 1s do I have? As many as Z1, right? So the sum of all the elements of a row adds up to 0. So there is one 0 eigenvalue of this Laplacian, which is basically a uniform translation of the body force. So if I say, like, the total body force imposed, like a center of mass. So if I subtract it off, all of the other eigenvalues are negative, so we can happily invert this. So what we, and I can show you some results, but basically the upshot of this lecture is that we actually have now a formalism and the discrete Laplacian is the generalization of the diffusion operator that we saw in the Q model case. But the diffusion operator and the Laplacian have very different properties. So in the sense that if I have a random underlying network, and if I look at these Laplacians, and I ask what do their eigenvalues and eigenvectors look like, their eigenvectors can actually be localized. So what this is saying I have hopping, but I have hopping on a disordered lattice, if you want to think about it. The Laplacian is like saying I have a random walk, but it's on a disordered lattice, and it's well known. So people who know about Anderson localization, the title of his paper was Absence of Diffusion in a Random Network. So you're diffusing, but you're diffusing on a random network, and you can get localized. So the point is that if I have, given the nature of my underlying network, I could get eigenvectors that are localized, which would then lead to phis that are localized and would give to localized responses. So we are too late in the day for me to say too much about what we are doing, but so modulo subtracting off that the uniform translation mode, I can write I can sum over all of the eigenvalues except that first one, which is 0. That's right, yes. So that's my formal solution to the response of a system, and the lambda i's are the eigenvalues and eigenvectors of this Laplacian matrix. Okay, and because all of the ones that are, I have summed only over all of the ones that are non-zero, I'm fine. So then what we are saying as a theoretical formalism, so there are a few important things to say. One is that given a set of body forces and given an underlying network, the response is unique. There's only one solution to this. If this solution now violates, let's say, some of our other conditions, like the torque balance and the Coulomb condition, which we haven't put in, then we can infer that the network necessarily has to rearrange. What it's saying is this network with force balance, if I poke it here, this is going to be its response. If this responds, then I fold it back into and I calculate the new contact forces and I find, oh, it's violating torque balance or it's violating my Coulomb condition, then I can infer that the network has to rearrange. If those conditions are not violated, then the network will not change, and this will be the new response. Okay, so that's one thing. Second is out of this set of lambda i's, these eigenvectors, there are some that are always localized. And I actually know very little about the nature of eigenvectors of this graph Laplacian. So I'm hoping to learn more from people, and we have just started doing this. But in all of the ones that we have looked at, there are some eigenvectors that are localized, and I'll show you one. And as soon as that is true, then there will be some component of the phi that is localized. But it's not as simple as saying I have a wave-like propagation or a diffusive propagation. It's not this or that. It really depends on which eigenvectors have a large overlap with the perturbing force that I'm putting in, which eigenvalues are small so that they dominate this sum. So it's a much more complicated story. So maybe that's not the best way to end a lecture. It's a much more complicated story. But there is always generically going to be some localized states in these in this spectrum. So let me end just by we've just started doing this, so it's all new stuff that you guys are hearing that. So this is calculating. So taking some. So where do we get these graph Laplacians from? I have no way of constructing them from some basic knowledge. That's not what we have any predictive. So these graph Laplacians are coming from people who do simulations or people who do experiments. So Agil can give me a contact network and I can construct this Laplacian. So this is a Laplacian taken from simulations of a sheared frictional system. And then we put 3 body forces on it. The red arrows, they are blown up. The perturbing forces are actually very, very small, but just to show them. And we put it this way so that the total body force is 0, so that I don't have this uniform translation. And what you're seeing is, no, 3 grains, 3 different grains. So we put 3 body forces on 3 different grains that are very close there. But we put it so that they sum up to 0, so that there's no total body force. And this is the response that you're seeing. And what you do see, and we've plotted only, I haven't plotted the vectors here, just the lines are just showing you the thickness of the magnitude of the force. And you do see this so this is not, the forces are now not computed from numerical simulations. We just take the graph Laplacian, we put this body force, and we compute this. And this is what you see, and you do see these regions of large forces and regions of small forces. And let me see if I have a picture here. And here is a picture of the lowest. This is actually for a different system. This is for the frictionless system, which is here. So even for the frictionless system, we do, so there is, for the frictionless system, it's much more isotropic. It's not sheared or anything, but you do have regions of large forces and regions of small forces. And if we now look at the spectrum of the graph Laplacian of that configuration, then this is a plot of the lowest eigenvalue, highest eigenvalue, and this is a plot of the lowest eigenvalue. So what I'm plotting are, so these lambda i's are again vectors situated on every grain. And so what you see is the highest eigenvalue is localized, and the lowest eigenvalue is not. Okay, so how much? So there's a whole range of these. This is completely delocalized. This is very much localized and far away. It's localized far. So this has no knowledge of where I'm putting the external forces in, right? So this has actually not very much overlap with those 2 forces, but has some overlap with this. Yes? For which one? No. No. So I'll show you. This is for the frictionless one. This is the density of states. It doesn't look like the Hessian. The Laplacian has nothing to do with the Hessian. It has not necessarily. The Hessian is a very different beast. The Hessian, I have to say, I have some interaction between them, and I'm looking and I'm expanding the potential around it. This is just an adjacency matrix of a graph. It has no knowledge of whether I have soft potential or hard potential or nothing.
So the edge you were
Yes, so it's not clear. I would be interested in the left edge because but the eigenvalue spectrum is so flat here that we could get we're getting the largest contributions from here. So it's not clear if exactly. It depends on the F body. So so it's almost 3:30. But this is where we are. But I think this is one of the most promising ways of thinking about stress transmission, and happily Jean-Philippe thinks that way too. So which is because what we are saying is you could not. So you need to impose vectorial force balance. So the force transmission in these granular systems is the nature of it is being completely dictated by the constraints of force balance, but it has to happen on an underlying disordered network. And the other nice thing, what appeals to me, is that now I have mapped it onto things that other people know a lot about. There's an ensemble of random matrices that I can create for an ensemble. And I have boiled the problem down to looking at the spectrum of looking at the spectrum of these Laplacians and looking at how the eigenvalues are distributed and whether the eigenvectors are localized of this class of random matrix ensemble. So that's where we are. We hope to push this far and see what's going to happen with this and what results we get. So let me just end there.